All right, let's dive into a physics mystery that you've probably seen 1,000 times, but maybe never really thought about. It's something that happens on pretty much any rainy day, hiding in plain sight. You know exactly what I'm talking about, right? You're driving along, you look out the window, and the rain isn't just falling down. It's streaking across the glass, coming at you at a weird angle. But if you were just standing outside, it would look like it's coming straight down. So, what gives? Well, that's the puzzle. And it's not some kind of optical illusion, it's real. And solving it actually uncovers one of the most fundamental ideas in all of physics. The idea that how you see something move depends entirely on how you are moving. This is the key. You have to get your head around this one simple fact. There's no single true way for motion to look. Your own movement completely changes how you perceive the movement of everything else. And once you get that, the whole rain puzzle just clicks into place. Okay, so to really unpack this, we need to talk about a concept called frames of reference. Now, I know that sounds a little technical, maybe a little intimidating, but it's not. It's actually a super simple way of asking, whose point of view are we talking about? Let's break it down. You've got two totally different realities here, and believe it or not, they're both correct. If you're on the ground, your frame of reference is stationary. You're not moving, so the rain just falls straight down. Easy enough. But inside the car, you are the center of your own little moving universe. From your point of view, it's the world that's rushing past, and the rain is moving relative to you, not just to the ground. So that's all a frame of reference is. It's just the fancy physics term for your point of view. Whether you're standing still, driving, flying in a plane, you are always observing the world from your own unique frame of reference. So how do we actually jump from one point of view to another? If we know how the rain is falling for the person on the sidewalk, is there a way to calculate what it looks like for the person in the car? Oh, you bet there is. And physics gives us a really simple tool to do it. The core idea here is surprisingly simple. If you want to figure out how fast something, let's call it object A, seems to be moving from your perspective, object B, you just take object A's real velocity and subtract your own velocity from it. And here's what that looks like as an equation. The velocity of A relative to B equals the velocity of A minus the velocity of B. For our puzzle, this means the velocity of the rain from the car's point of view is equal to the rain's true velocity minus the car's velocity. It's really that simple. Now, since velocity isn't just about speed, but also direction, we use these things called vectors, which are basically just arrows. And here's the cool trick. Subtracting a vector is the exact same thing as just flipping it around 180 degrees and adding it. So we're going to take the rain's velocity arrow, take the car's arrow, point it in the opposite direction, and then stick them together. Okay, let's do it. We have the question, we have the tool, it's time to put it all together and finally solve this thing. This is the big aha moment. First things first, let's be clear on what's what. The thing we're watching is the rain, so that's our object A. And the observer, well, that's us in the car, so we're object B. So vector number one, the rain's true velocity, VA. This is what it looks like from the ground, our stationary frame of reference. The rain is just falling straight down. So we've got one arrow pointing down. Next up, vector number two, the car's velocity, V sub B. Let's just say we're driving forward, and we'll draw that as an arrow pointing straight to the right. And now for the magic. We just plug these into our formula, VA minus VB, and remember what that really means? We're going to add the downward rain arrow to the opposite of the car's arrow. So if our car's arrow was pointing right, what's the opposite? Left. You add that new left-pointing arrow to the rain's downward-pointing arrow, and what do you get? A brand new arrow that points down and to the left. And that is it. That diagonal line is the path the rain appears to follow from inside your car. That's why it hits the window at an angle. Puzzle solved. So, okay, this is a pretty neat trick for understanding why rain looks weird, but does it actually matter in the real world? Well, it turns out this idea of relative velocity isn't just a fun little puzzle. It is absolutely critical for how we navigate our world. Think about a pilot trying to land a plane in a strong crosswind. They are solving the exact same kind of relative velocity problem we just did. So are sailors, who have to figure out the difference between the true wind and the apparent wind that's created by their own boat's motion. Your GPS is constantly calculating the relative velocities between your phone and satellites in space. And astronauts, they live and breathe this stuff when they're docking with the space station. It is literally everywhere. And that kind of leaves us with one last big mind-bending question. We just proved that motion is totally relative, right? Your reality in the car is just as valid physically as the reality for the person on the sidewalk. So, it makes you wonder, is anything ever truly standing still? Or is everything in the entire universe just moving relative to everything else? That's a pretty deep thought to chew on the next time you're just watching the rain fall.